really good reason of learning it. So you should hear it from, what is the expression, from the horse's mouth? So the person who...
Okay.
Mike is lead DSP guru at Dolby here in Australia, and he will show you what miracles FFT and convolution can do. And of course, Steve will then tell you what wonderful internship opportunities there are at Dolby, but for those who do well in this course. How about that? So, Mike, please follow.
Thanks, Alex. Well, with an introduction like that, yes, I'm from Dolby, Sydney, so that's up on North Sydney, and there's around about, 120 mostly engineers working on assorted signal processing and related engineering tasks. And Alex asked me to come along and convince you that the fast Fourier transform, which apparently you studied, I guess it's early this year, you've been quick getting through the course, is something that's actually practically useful, and not just practically useful, it's actually incredibly important to actually turning a lot of the processing you want to do, both on sound and vision, into something you can fit onto the devices you have in front of you or in your pocket and that kind of stuff. So today, I'm pretty much going to begin with an introduction to audio signal processing to kind of give you a grounding in the kind of stuff both Dolby does and the general field about where this kind of signal processing fits. And then I'm going to jump into a couple of case studies to talk about a technology called headphone virtualization, where we can talk about a very explicit example of where fast Fourier transform enables a piece of processing that you might be familiar with. And then perceptual audio coding, which is a bit of an insight into, I guess, one of Dolby's other big businesses, which is how to compress audio so that you can transmit it efficiently and store it efficiently and still listen back to it and have good quality experiences. But, starting with kind of the business view of where audio processing fits within Dolby, you can start with the big screen. And these days, Dolby does even more on the big screen. Dolby's branching out into vision and image processing, and you may have started to hear brands of Dolby Cinema, which is a high-end cinema that uses laser projection and high dynamic range, and Dolby Vision, which is the high dynamic range technology that's going into TVs and delivering really vibrant images to the home. But we're still initially started as an audio company. And if we look at what we do in the audio space inside cinemas, most of you are probably familiar with the idea that cinemas use multi-channel audio. Usually kind of a 5.1 channel surround sound is the experience you get at most cinemas, although you might go to a high-end cinema and get 7.1, or these days go to a Dolby Atmos cinema that supports object audio. The whole task of getting that audio from the 5 channels that it gets packed up into and played out in the speakers in the cinema space itself takes a little bit of signal processing. I mean, some of the things you have to think about is, you think about a multiplex cinema, you've got 8 or 12 cinemas all in the one complex, and they don't buy that many copies of every movie. In fact, movies these days are essentially hard drives full of data. And so you've got to ship the data around between the cinema master library and the actual cinema projector that's going to put it up in screen 1 or screen 3 or whatever. So there's a lot of coding and transportation work that goes on to pass around the audio and the vision that sits in that side of just getting it from one end of the room to the other end of the room inside of a large cinema. Then when you get it inside the room, if you look around, there's usually dozens of speakers maybe. And if you think, hey, well, does a 5-channel piece of audio come out of 30, 40, 70 speakers inside a cinema, you realize a lot of those speakers must be playing the same part or the same track. But if we did it that simply and you played exactly the same thing out of all the cinema speakers, even all the cinema speakers down the left-hand wall, you played exactly the same thing, it doesn't sound so great. You get things like spatial combing happening and interference between the waveforms from 2 adjacent speakers. You've probably all seen double slit experiments with interference patterns of waves. Happens in sound, so you want to avoid it. So there's technology that goes into processing the audio to play it back in the cinema space. When it comes to Atmos, which is that step away from defining a movie's sound in terms of channels and turn it into individual objects and be able to have a kind of helicopter take off and fly across the ceiling and out the back end of the cinema, the way that that gets panned across all the speakers in the cinema needs to be calculated based on the cinema you're in. Because if you're in George Street, you've got a different set of speakers than if you're, say, in the home office in San Francisco. Different number of speakers, different locations within the space. And we want to customize the playback and the panning to make sure it comes out of the right speakers at the right time as it plays. So that's called rendering. And the rendering of the soundtrack in Atmos is another big part of how we have to do signal processing, audio signal processing to get that playback right. Then, if you drill down into what else happens inside the speaker system of cinema, you've got individual speakers that don't match the ideal textbook definition of a speaker. You know, in a textbook, you might get told that a speaker is a nice, flat, equally able of producing sounds at 200 hertz as it is of producing sounds at 20 kilohertz. But when you measure a speaker, it's a physical device. It doesn't work like that in reality. So we have to do work to try and make those speakers sound as good as possible. And that's kind of equalization and at the same time protecting the speakers from over voltages or being overdriven. So there's a heap of signal processing that goes into kind of the equalization and loudness management and speaker projection algorithms in those speaker arrays in the cinema. So just sitting in a cinema, you've got a heap of signal processing going on, which is nice and well hidden if we're doing our job right. Take a cinema experience and decide you want to deliver it to the home, whole new set of problems arise. One of the classic things is the size of the audio in a cinema is uncompressed. Highest quality, they don't want to put any losses in it, they want to make sure it's full dynamic range, they want it to sound as good as it possibly can. But if we try and ship that to you, or give it to you on a disc, it doesn't fit. So there's a big effort around reducing the size of the movie that we deliver. Both the video and the audio needs to go through compression. So some of that's perceptual audio coding, and we're going to do a case study on that later. Some of it's things like matrix encoding. So a few of you probably have heard of ProLogic or ProLogic 2, which is where 2 channels of audio get upmixed into 5 channels of home theatre. And that's a particular signal processing problem. How do you encode onto 2 channels of audio a multi-channel signal? Multi-channel audio coding is the idea that you can both code within a single channel to reduce redundancy, and you can look at the relationship between channels to find redundancy. So there's extra coding tools that come into play. Another task that is less, I suppose, conscious in Australia because we tend to only deliver in one language. But if you go to Europe or if you go to America, you find you're delivering programs with lots of languages. Simultaneously, you want them all in the same bit stream, you want them all delivered at the same time so that the user can flick between the languages they want to hear. You also, I mean, in Australia, it might be more common that you want to flick between the language or the dialogue of the movie and the director's commentary or something like that. So how do we pack those into the same pieces of bit streams? So that's another area where we're doing extra signal processing around delivering a movie theatre experience back into the home theatre. There's also the need that one bit stream needs to come out of multiple devices. It wants to play out of your mobile phone, mono, plug some headphones in to get stereo, or plug your tablet or your mobile phone into your AVR at home and get your full home theatre 5.1. We'd preferably not want to have to do 3 different encodings to deliver that. We want it all delivered in one nice, neat bundle. So there's lots of extra little tasks that signal processing has to kind of come to the fore and solve in order to provide the home theatre experience. The other thing, the other area that you think about when you think about broadcast is switch away from thinking about the movie you're watching in the cinema and think about the footy game that you want to watch on the weekend. Or if you're like me this weekend, Melbourne Grand Prix, you know, how are we going to capture and deliver a live event across audio, and what kind of things happen with that? Big things change in terms of how much time they get to mix that content, how they have to deliver it and distribute it across Australia, even if we think just Australia. The ads that we're going to play in Sydney are going to be different to the ads in Brisbane and Melbourne. So all of those kind of questions about the experience need to be coped with by the signal processing streams that go on. So how it gets mixed, how it gets delivered, how it gets encoded, how there are breaks put into it so that it has ads put in, can have ads inserted. And indeed, one of the biggest challenges and one of the biggest tasks of broadcast is making sure it's all at the right volume so that when the ads come in, they're not at a distinctly different volume from the program you're listening to. So you're not sitting there watching your program and then the ads come in and blow you out of your seat. And in fact, there's interesting bits of legislation around CarMax and loudness control that make sure the broadcasters actually have to not let ads be super loud compared to the rest of the program. So how do they know all that stuff? Well, we've got to do some signal processing to help them understand loudness during broadcasting. So all of that stuff kind of brings high-end entertainment into the home. But of course, most of you guys don't watch TV anymore. It's the reality. Most media these days is consumed either on mobile phones or on tablets, by far. Massively swamps out what used to be watched on the family TV. So we need to think about what happens when we start looking at these little devices. The biggest thing that changes is while in your lounge room or on your old TV set, you might have nice, reasonably sized speakers that can produce good sound. Think about the speakers that are on your mobile phone. They're not the best. That's probably being generous. How do we make them as loud as possible, but keep them as clear as possible? All right, so now we need to start understanding how do these different types of speakers behave. So similar to the cinema case where we've got non-ideal speakers and we want to equalize them, now we've got little speakers that, again, aren't flat, but if we try to make them loud, we're going to start making them distort as well. So we need to start trying to protect them from distortion and overheating because they heat up very quickly, they're very small devices. So there's a whole heap of post-processing we can do to try and improve the sound quality you get out of the devices you're listening to. Now you're thinking, okay, sometimes I watch my tablet sitting in bed, right? That's one listening environment, but what if I'm on the bus or on the train? Well, the characteristics of the noise in those situations means listening to the audio is harder. So what can we do to help you hear what's happening on that content better? And again, there's tricks for us to play with. There's ways for us to analyze loudness and make sure that the really soft sounds inside your audio don't disappear, so we bring them up. But at the same time, we don't want the louder sounds to get super loud and blow your eardrums out because you've got headphones in. So we compress the dynamic range. This isn't about data compression, this is about loudness compression, so you can listen to it in adverse environments. All of these tricks and processing techniques rely on signal processing and the ability to do this kind of stuff both on limited devices and in real time. And really that's kind of the overall story that this comes up to is signal processing, when you think about in the world, most of it happens in real time when it comes to entertainment, and most of it has to happen in a power-constrained, battery-constrained style world of a mobile phone or a tablet. Another important area, and perhaps not as important for you yet, but will be important to you very soon, is the idea of voice communications. And maybe these days you use Skype to talk to a friend on the far side of the world. When you get out into business, if you're working in a large organisation, you're going to start trying to have conversations with 20 or 30 people in the room across conference calls that might handle 2 or 3 different geos. Trust me, this is a task that is hard and difficult to get right because multiple people speaking at once, all trying to share the same telephone line, or in this case, VoIP line, starts to have all kinds of interferences going on. At the same time, it has to be able to be mixed and go out onto an old style PSTN line or old telephone line. And so there's this whole subsection of audio processing which we talk about as voice processing. And voice processing is focused around that whole idea of if the audio isn't kind of a full cinematic music score plus sound effects and special effects, what if it's just people talking? What can we do? What special things can we do to make sure we get the best experience there? And that's a different set of challenges, but we have different rules that we can apply and different models of speech that come to play within that signal processing domain. Again, a lot of it still relies on your basic signal processing, and trust me, Fourier transforms exist in all this space as well. But the task at hand is subtly different. And you know, when you come to think about where the one of the most important areas of improvement or value in terms of a business is concerned, business people talking to other business people around the world across conference calls is actually a huge business. If you look at some of the big telcos in the world, people like British Telecom, there's a massive amount of infrastructure and money involved in trying to get good communication between different entities around the world. And so getting a good experience is another challenge, but you know, worthwhile if you can do it. And you know, from that perspective, Dolby has technology in all of these areas. So Dolby Voice is our business conferencing solution. We have Dolby Audio, which is your standard 5171 home theatre style system. We have Dolby Atmos, which is our cinema objects through to home objects these days. We have Dolby Vision, which is the high dynamic range image stuff that's coming out now. So we touch on almost all of that at some point within the Sydney office, in little bits and pieces. But for now, we're going to focus in on just the audio processing side of it. And I thought the best way to give you some context to the processing is to start with the basics. Really, every audio signal processing system can be represented with three basic blocks. At some point, there is a sound wave in the real world, and we need to bring that into a domain where we can do computation on it, and then we're going to play it back out to the real world for someone to listen to it. So we've got an analog sound wave, gets captured by a microphone, needs to be converted to digital, and we use an analog to digital converter to do that. We can then have our digital signal processing go to town on it, do anything it wants with it. And then when we're finished, we've got it formed back up the way we want, we can play it back out through a digital to analog converter, hits an amplifier, hits a speaker, and you can listen to what's happened. Now, sometimes that analog to digital conversion and the digital to analog conversion are opposites on different devices. If you think about a telephone call, the A to D is sitting on the call talker's end, and the D to A is sitting on the listener's end, but everything in the middle is just bits and numbers, and we can do all our signal processing on that. If we think about that then, the most important question we need to make sure we get right is when we go from analog to digital, we need to get all the information, and we need to get it correctly. And what does correct mean? Well, we're going to sample the information, so it's basic sampling theory, and the questions of how often do I need to sample it and how precisely do I need to sample it are the two that we need to get right. If we stuff those up, we lose valuable information and you can't recover it later. So the first question of how often do I sample it falls under this heading of sampling frequency. And you may have already seen this, I know, in some other signal processing course, but basically the question you're asking is, how many times per second do I need to look at the waveform and sample it, or take its value? We go back in information theory, and Nyquist was a guy who knew a thing or two, and he basically pointed out, if I've got a sine wave, I need to look at that sine wave twice within its period in order to make sure I get it correct. That's essentially where Nyquist's sampling rate comes from. It says 2 samples per period, or twice the highest frequency. Now, why does this work? Well, it basically works because, as well as saying this is how often we need to sample a sine wave, we know that we can construct pretty much any signal we want, or most of the useful ones anyway, by summing together sine waves. So if I've got a heap of different sine waves and I've sampled them all according to Nyquist's sampling theory, I should be able to reproduce the signal of interest. So sampling frequency is pretty straightforward. The harder one, or the one less thought of, you'll have a million questions about sampling theory in your engineering life, but the one you often don't think enough about is resolution, or how precisely do I need to sample when I look at that signal. On the left here you can see, hopefully, a bit of a diagram that shows you if I have an analog axis and I'm trying to turn it into a digital axis, so a 0 or a 1, I've got a whole continuous range of possible input values, -1 to +1. Let's assume I've done my scaling already. And so I have all these pink dots that I could be looking at. But depending on which pink dot I choose, if I turn it into a 0 or I turn it into a 1, I'm introducing some errors. So all those little pink arrows represent kind of the error associated with each one of those samples. So quantization, as the name implies, means throwing out some details. We're not going to be able to keep all of the information that was in that continuous value. But that's usually not a big deal. If someone comes and asks you how tall you are, you don't usually give them the value down to the micron. You just round it off around centimetres. It's good enough. So the question of how much quantization error can I bring into the signal becomes a question of, well, how many will be good enough for the purpose I'm interested in? So there's a bit of maths behind this, and there's a link there if you want to go and have a look at the maths, but I'll skip over it. The basic rule becomes every time I put another bit in my quantizer. So I start with a 2-bit quantizer. So in a 2-bit quantizer, there's 4 quantization levels. If I add a 3rd bit, so I go from 2 bits to 3 bits, I now have 8 levels of possible output. By doing that, I reduce the the signal to quantization noise ratio by 6 dB. Now I add another bit, I reduce it again by 6 dB. So dB is a log scale, and that's why, in this sense, it's linear in the dB space. So every time I add another bit, I reduce my quantization noise by 6 dB. That's a rule of thumb. It does rely on a couple of assumptions, but the assumptions aren't terribly bad. And you can use this as a design rule to help you decide how many bits do I need in my quantizer. So let's design sampling for audio. We now know we've got 2 questions to answer. The first is what frequency, what sampling rate? And to that end, we need to very simply ask the question of, well, if this is audio, this is something we listen to. The definition of how much we can hear in the frequency range will lead us to the answer of what our sampling rate should be. So if I tell you that human hearing, if you're young and healthy, you can hear up to around about 20 kilohertz. If you're old like me, you're starting to lose the high frequencies pretty quickly. But good hearing, normal human hearing is considered 20 to 20 kilohertz range. So if I said that to you, what kind of sampling rate do you think you're going to need? Anyone want to have a guess? 40 kilohertz. I'm hearing 40 kilohertz. That seems good. Yeah, I think Nyquist has come along and say, yeah, if I want a 20 kilohertz band limited signal, if I sample at 40 kilohertz, I'll cover it. Now, how many? I did hear another number shouted out over here somewhere. 44.1. 44.1. Where's that come from?
That's most of my audio.
Most of your audio is 44.1. Do you know why? No, the full range of the human ear is 20 kilohertz. Yeah, that's what we've already said. So why would you want an extra 4.1 kilohertz in your sampling rate? Any ideas? Something about easier to encode?
Quality of the signal?
Quality? Which bit of the quality?
In terms of if you have a higher sampling rate, you're going to get a more accurate reproduction of the...
But I can't hear the difference. That's the point, is once I've got above 20 kilohertz, I can't hear the difference. Yeah?
If you have a frequency that's just slightly less than half of the sample rate, you get an alias speed of like the amplitude decaying and then coming back up.
Yep, and so do you know what the next step of that logic is?
You oversample.
Oversample. All right, so you're on the right track. If we were to only use 40 kilohertz as our sampling rate, and that's what Nyquist says we should, we've got the slight problem of can we correctly and accurately sample the 20 kilohertz frequency. Now, if we look at the frequency domain and we try to say, well, if I'm recording with a microphone, I'm getting all the frequencies. My microphone will pick up all the frequencies, those above 20 kilohertz as well. So in order to get something that I want to sample, I'm going to want to throw away or filter out signals above 20 kilohertz. But I can't do it with a brick wall. Most of you are kind of getting used to the idea that you don't want a mathematical function with an absolute discontinuity. You can't create that either in a piece of electronics or in a bit of maths. Because if you try and create what we call a brick wall filter that says, let everything up to 20 kilohertz through and throw everything above 20 kilohertz away, you just can't build it correctly. There's no way of realizing that. So what you actually have to build is a little filter that has a low pass characteristic, passes everything below 20 kilohertz, and then rolls off. And that roll-off space is to avoid that beating or that aliasing of stuff back down, but it's going to take some frequency to go from pass to stop. So we have to put a guard band in. 44.1 kilohertz is about having a guard band so that we can correctly reproduce 20 kilohertz, but we have also given ourselves the low pass space to get rid of the higher frequencies, those at 30 kilohertz and above. Still come back to the question of why 44.1, because 44.1 seems like a reasonably odd number to choose. I'd love to be able to stand here and say the absolute reason 44.1 was blah. No, you've got a reason for 44.1? What have you heard?
No,
Oh, sorry, question?
sorry, just a question, yeah. If you're sampling at 44.1, then presumably 22.05 is going to be, perfectly sampled. You've got just samples at the peaks and troughs.
Yep.
Assuming it lights up with your
Yep.
in phase. Once again, if you've got a frequency that's slightly less or slightly more than that, surely you're going to get an amplitude beat.
You do, but provided your amplitude beat is sitting above 20 kilohertz,
Would you not get that with the lower harmonics at the same?
they're going to start dropping off because what we actually do, let's see whether I can draw a picture that makes sense.
You get it. Yeah. 11.025.
So you've kind of got a low pass, I don't know whether that's visible. You've got a low pass which passes everything up to 20 kilohertz and then starts throwing away frequencies. By the time you get to the 22.5, you've thrown away a heap of content. By the time you've got up to, this would be the reflection point, you've already thrown away most of the energy. So the fact that you do the filtering, the anti-aliasing filtering, before you do the sampling, is why you don't hear that stuff.
But what if you pass the 23.05 and then go a little under or a little over that?
You could theoretically hear it. Absolutely. Yep. Yep. Oh, I love Wikipedia. Excellent, excellent reference. What's their answer?
44,100.
Yep.
The product of the first 4 prime squared.
Right, which is a great number. And who knows? It might be real. I personally prefer the urban legend that says that was the sampling rate required to get Tchaikovsky's 1812 to fit on one CD, and it was made by the Sony executives. But it's a bit of a lost in history kind of number. So I love that Wikipedia's got this awesome, prime squared things. Sounds awesome. Sounds great. But the other numbers you see is if you look at Blu-ray, and this is when if you look at the audio that's associated with movies, you'll often see most of that sampled at 48 kilohertz rather than 44.1. So 44.1 is kind of CDs. 48 is what you expect in a movie.
Is there any chance you can turn off the lights?
Alex, is there any chance I can turn off the lights here? Sorry, are you having trouble hearing me?
I'll just turn it down slightly, like it's slightly too loud, like it's
I'm speaking too loud. I can do that.
feedback.
Too many 44.1s? I can lay off the 44.1s, okay. That's a bit easier. Oh, okay, now we're going to put everyone to sleep. The mood lighting's in, all right. All right, let's get back to the second question. So we've answered the sampling rate question for human perception. Now we get to ask the harder question about precision. How many bits per sample should we use for listening to sound or capturing sound that we want to listen to when we play it back? So a couple of relevant numbers here for you. If we look at the Bell scale of loudness, we set the threshold of hearing at 0 dB, and then we've got several points along this scale that kind of people use to reference how loud things are. So you may have seen some of these before. If you stand near a jet engine, you're going to want 110, 140 dB is what you're going to hear. Very loud, damagingly loud. If you're standing beside the road, standing out here on Anzac Parade, 100 dB you're being exposed to. As far as workplace health and safety, if you're working in a factory environment, you're working in a loud environment, if you're under sustained 85 dB or louder, you have to have hearing protection. So that's to protect your hearing. So sustained exposure to 85 or above is kind of long-term, potentially damaging loudness. What does this all have to do with our decision about how precisely we need to sample audio? Anyone have an idea of what sampling precision we use for audio? 16 bits? Do you have any idea where the 16 bits comes from or how it relates back to these figures?
Didn't you say earlier that every bit's at 6 point something decibels?
Yeah, 6 dB of noise reduced by each bit I add. So if I can hear sounds down between, basically across a range of up to 140 dB, the louder sound to the softer sound is my practical hearing range. If I have quantization error that's less or covers less than that range, then the noise that's introduced by quantization shouldn't be able to be heard. So essentially that 16 bits gives what we call 96 dB of dynamic range. Now, that 96 dB isn't as large as our dynamic range available to the human ear. Is that a big deal? Probably not, because if we go from 0 dB, so if everyone was deathly silent in this room, we all tried our best to make no noise at all, how loud do you think this room might be? Yeah, it's roughly 20-ish. Probably a bit over 20 actually. The fan in here I can hear quite clearly, even over the noise. So your background noise level is usually much higher. In order to hear kind of 0 dB, you're going to need to be sitting in a specially treated anechoic chamber and have really quiet environments. So in practice, we never get down to really quiet, silent environments. And at the same time, if 110 to 140 dB is painful, we really don't need to capture it. We don't want to reproduce sound with that much noise in it or that much volume in it. So we only need to kind of cover the useful practical range. And 16 bits does that quite handily. Mind you, if you, again, 16 dB, that's what you'll find on CDs. 44.1 kilohertz, 16 dB, 16-bit samples, there's your CD quality sound. But if you look at some other environments, you'll find 48 kilohertz, 24-bit sounds being sampled. So at 24 bits, you get 144 dB of range. More than that, and you really are just adding bits that you're not going to be able to be heard. Similarly, 44.1, 48 kilohertz sound, sampling rates. I'm not sure how many of you pay attention to other things. I have seen adverts around high sample rate audio, things like Tidal as a music service, who promises to deliver up to 192 2 kilohertz sampled 32 bits per sample audio to you. So why are they even interested in that? Any ideas? Absolutely can market it. I can sell you this audio. It's twice as big and it's got twice as many bits, and surely that's good, isn't it? Might be a bit snake oil-ish.
Maybe like for research applications or like non-listening applications?
Sure, yeah. If I wanted to do sonar analysis or radar analysis, I might want to be sampling higher, but then I'm not doing audio processing. So these things about dB of human perception and frequency range of human perception is kind of where we're modifying the purpose here. But it's definitely, there's definitely valuable practical applications outside of audio where you need higher sampling rates.
You want to listen to it like really slowly.
Yeah, that's an interesting thought. Why would I want to listen to something really slowly though? Editing? Now we're on the right track. What happens if I want to modify it? What if I want to process it? We know whenever we do multiplication or any operation inside a digital domain, we're not using pure maths, we're using discrete maths. And so whenever we do any kind of processing or editing or modifying of a signal, we're going to introduce some more noise. Now, if we make sure to begin with we've got a bit extra dynamic range to work with, then the noise we might introduce during the processing stage, we can keep outside the audible range. If we only had the barest perfectly sampled thing, and we started even applying some simple processing of it, we run the risk that the processing will introduce artifacts we could actually hear. So you often find the high sample rates and the high bit depths are sitting inside professional mastering environments. So if you go into a mixing desk or you go into a mastering environment where you're doing recordings and you know you're going to mix and remix and remaster stuff, you want to have that captured at a higher precision and a higher sampling rate because it gives you some slop to muck around with. You know, you might record the guitar at one level and the vocal at a different level. Even just the process of matching those levels means you've done a bit of processing. So you want a bit of extra guard space around it. So professional environments might use higher sample rates and higher bit depths because they're going to do work with the signal before they present it. And yes, if you're wondering, we definitely do higher sample rates and high bit processing within some of the stuff we have to do for things like cinema presentations of Atmos and that kind of stuff. So then, before we've kind of finished the basics, couple just, I suppose, facts or numbers to keep in mind. We said 48 kilohertz, 16 bits per sample. So what data rate's that? So it quickly turns into 768 kilobits per second per channel. Think about a 5.1 audio track for a movie that lasts 2 hours. That's 286 gigabytes of audio. By the way, your DVD only carries 4.7, so we're going to have to heavily compress your video. I hope you don't mind. It's kind of pointing out that if we don't do anything about this data rate, it's actually quite high, and we need to do some compression and some reduction somehow. The other thing that's important to think about when you think about audio signal processing, like most signal processing, this idea of sampling and working on those samples directly falls under an area of processing called time domain processing. Time domain processing is very useful. There's lots of stuff we can do there, but there's also lots of stuff we can't do there or we can't do there efficiently. So things like the Fourier transform are ways of taking our time domain system signal and representing it in the frequency domain. And a lot of the processing we do, a lot of signal processing in audio particularly, is done in the frequency domain. So fast Fourier transform is an efficient way of doing a Fourier transform, and it's very important to being able to process in an efficient way. There's other signal processing transforms that you'll come across, particularly if you go look at JPEG or something in image compression. In image compression world, they use a lot of discrete cosine transforms, which is a cousin to the Fourier transform. So, we think about these two different domains quite a lot and whether we're doing the processing in the right domain and being able to understand how an operation behaves in one domain compared to the other domain is useful for being able to understand why things can be done efficiently one way or the other. And I think with that, I've pretty much covered what I'd consider the basics of audio signal processing. We know how to sample a signal, we know why we chose the numbers, and we've highlighted that kind of this time versus frequency thing is useful from a processing area, and we have a basic understanding that we've got a lot of data there if we don't do anything special with it. So let's have a look at some of the stuff we can do. So the first case study is something called Headphone Virtualization. So this is actually something that my team has been working on now for a bit over 2 years, specifically, around how we can apply headphone virtualization to the Atmos object audio space. But the basic problem as we look at it is going to be, if you are wearing a pair of headphones, can we make it sound like you're sitting in your living room with your full speaker system? Or can we make it sound like you're sitting in a cinema with all of the speakers that are sitting in a cinema? So basically the task we want to achieve. We want to make you feel like you're not just sitting there with a pair of headphones on. Why wouldn't you want to be sitting there with a pair of headphones on? Mostly, I don't know how many of you have done this and really thought about it, if you're listening to stereo, and whether this is old stereo music, go and grab a Beatles track, or a stereo down mix of a movie, and you're listening to it, the sound is very much inside your head. It's internalized. All the sound seems to be happening inside your head rather than out in the world around you. So some people describe this stereo pressure as kind of a claustrophobic space, and it doesn't give you a good sense of something is over there or something is over there. Now, why is that important? Well, people like that feeling of not being claustrophobic and having this nice big space that they're sitting in. But if we think forward to kind of the applications that are kind of hot these days, virtual reality is an example of where the whole point is to trick your mind and your senses into having an environment around you. And if that happens visually, but all the sound ends up inside your head, you're not going to agree with it. Your brain's going to start kind of rebelling against that experience and going, oh, this doesn't feel real. So one of the tricks is to try and give audio that same sense of 3D that you get with 3D goggles. And so that applies to virtual reality, augmented reality. It's a useful trick for games as well if you want to know who's sneaking up behind you. So those are kind of why headphone virtualization is kind of interesting, and the basic job of we're trying to make this stuff sound like it's out and around us, not inside our head. So how do we achieve that? There's really two tricks we need to achieve to do that. We need to make it sound like the audio is coming from different directions, and we need to make it sound like we're sitting in a room. Right? So there's two steps to this trick. If we can pull them both off, we're going to succeed. Maybe that's a good point to pause for a bit. We've been sitting here for 50 minutes now, talking, listening. With those two thoughts in mind, do you guys want a quick break? All right. Why don't you take, 5-10 minutes? We'll start again on the hour. Okay, so we'll keep going. Right, we left you with the two problems of getting the headphone virtualizer to work. One, make things sound like they come from a specific direction. And two, make it sound like I'm sitting in a room. So one of them involves something we call the room impulse response, the RIR. And the other requires us to understand what a head-related transfer function is, or an HRTF. We're going to tackle the room first, because once we tackle the room, the HRTF's a bit easier. So, room impulse responses. Let's see whether I can get this to play.
Wait here, I'll find us seats.
Oh, no, we have seats.
Not the right seats.
Ha! Ha! Ha!
What is he doing?
It's finding the acoustic sweet spot.
Ha!
Does he always do this?
Sometimes he brings a toy xylophone.
Ho! Ho!
I am really sorry about this.
No, it's fine. You know, sweet.
My apologies, you've been sitting in it all along. Leonard, you want to slide over one?
No, just sit here.
Oh yeah, this is it.
Right. Well, you know. So what was he doing? He was trying to collect the impulse response of the room. All right. He was exciting the room with sound, measuring how the reflections came back, and pretending to be able to understand what it was. The key tricks or the key things that's going on there is an impulse response is how a space or room or a system responds to a single impulse. I mean, you guys all know that from circuit theory. Well, the same is true acoustically. You know, if I create an impulse, and you know, you can create impulses very simply, you know, snapping your fingers, clapping your hands, you hear kind of the echoes in the space. And that can be captured and used to describe the space's acoustic response. And if I'm going to use it, I can in fact turn it into a filter. So how many have seen the filter convolution equation written like that before? Some? Think back to the FFT class. Do we express the polynomial of interest as h, and you can write down the summation as the application of that polynomial in the convolution. So what does it look like? This is what you might get if you record a impulse response of, in this case, this was a lobby. So think about a lobby, hard tiled surfaces, big space, you know, thinking corporate entrance to a building. There's lots of reflections going on. So when we look at the impulse response, there's a few things you can see. First of all, I create an impulse at time 0, and before I hear it, there's some time that it takes sound to travel. So the direct path takes a little bit of time to get from the speaker or whatever it is I was creating it with, and the point where I'm recording it. In this case, it's about 6 milliseconds to do the trip. If you're feeling energetic, you can work out how far away the microphone was from the speaker. But once it arrives, we get what we call the direct path. So how did the sound change as it traveled towards me? Then, a short period of time later, we start seeing new spikes arrive in the impulse response. Those new spikes are the discrete echoes you hear off the hard walls. Right? You've stood in a bathroom, you've stood in a large, we're talking this reflective surface, and you clap your hands and you hear distinct echoes come back at you. So those are picked up and we call those the early reflections. Then after a while, you stop hearing distinct echoes and you just kind of hear mush. just this general reverberance of the space. And that carries on and dies down over time. And that's what we call the late field reverberation. All right, so we have an impulse response for a room. It includes the direct path that happens directly from the source to the recording point. You've got the first big echoes that come off usually the floor right in front of you or the wall closest to the speaker. And then you've got... It's okay. Then we've got kind of the mush or reverberant space that kind of gives you a sense of space. And if you're in a kind of carpeted, deadened room, these things drop off quite quickly and disappear because all the energy gets absorbed into the carpet or into the curtains. If you're in the hard surfaces, they last longer and hang around. That set of samples that we record, we can use as the impulse response. We can turn it into an FIR filter, and we can apply it as a convolution to the signal that we're trying to use to make it sound like the source was sitting in that room. Now, very importantly, when we think about this impulse response represents what I recorded from a single microphone based on a single speaker or single sound source in that space. If I was to move the speaker, or if I was to move the microphone, the impulse response changes. All right? So if I wanted to try and model the whole of the room and all of the different positions inside it, it's a vastly more complicated problem than having just one impulse response. Somehow we've got to capture a spatial impulse response for that room. That's tricky. We're not going to talk too much about it, just let's say it's tricky. But in the meantime, I can make that sound like it came from that position in my room. So for example, if I knew I was sitting on my couch or recording on my couch and I was playing this sound out of the front left speaker, I know that this is the impulse response to make it sound like the front left speaker's sitting over there. Now, how much of this impulse response do I need? It depends. Depending on the space and the size, it could last quite a long time. You can see this lobby impulse response lasts well out past the 100 millisecond mark. In fact, I had to cut this down. It lasts almost 300 milliseconds before it kind of really dies down. But if we say for most kind of rooms we want to listen to stuff in, we could keep just the first 50 milliseconds. So think up to around about midway through that graph. Keep that much of the impulse response. And that will give us a reasonable room sound. Do some maths quickly. 1440 points. That's at 48 kilohertz. And then we look at what it costs to do a convolution between a single sample or a sound sample and that 1440 points worth of impulse response. And we work out that we're running 69 megaflops to do this processing. So that's 69 million floating point operations per second in order to process a sound source through this filter. I don't know whether anyone has a good feel for whether that sounds like a lot or a little yet. Who says that feels like a lot? A few people. Who says that feels like a little? Sounds really cheap. Right, yeah, no problem. 69 megaflops, will happily fork that out. Well, let's turn those megaflop numbers into some useful numbers when it comes to processors. So if you've got a DSP, so a specialized signal processing chip, and it's got a single cycle MAC, multiply and addition, which is, this is what specialized DSP chips do. That means you've got 69 megacycles per second, 69 megacycles per second. If on the other hand you're using an ARM processor, we're now talking general purpose CPU, they don't have a single cycle MAC. Their MAC is around about 3.5 cycles. That means we're going to be spending 240 megacycles per second in order to process this filter. Oh, and by the way, did I mention we have a 5.1 signal? So it's not just one of these filters, we need 10 of these filters. So we need one for the left and the right ear for each position in the array of speakers. That gets us up to 2,400 megacycles per second. Does this sound expensive yet? Are I starting to make numbers sound expensive? I'll tell you, if you're running that on your mobile phone, you're going to be able to do that for around about 20 minutes at that that megacycle burning, if you were dedicating your mobile phone to running this kind of filter bank in its full convolution form, the battery life of your phone would be roughly 20 minutes. That doesn't sound like a good deal. We're not going to be able to sell that. Plus, that's not including the fact we want to play back a video at the same time. So. All right, so what do we do instead? We fall back on a little rule that we learnt back at high school, that convolution in the time domain is equivalent to multiplication in the frequency domain. And this is what we were learning when we were talking about Fourier transforms. If we can convert stuff using the Fourier transform, we can complete this convolution operation through a multiplication operation instead. To do it, we need to start doing block-based transforms. So we can't kind of have, we don't now have every sample coming in and processing every sample one at a time. We now block up the samples, take a block of samples, Fourier transform them, do the multiplication, invert the Fourier transform, and that gives us our output signal. What size block do we want to use? I'll keep it simple. We'll stick to 2048 block. We'll say our Fourier transforms cost is therefore order n log n. This factor k is where things get processor specific. So for an ARM processor, your k ends up at kind of 2.5, and your Fourier transform for the 2048 samples is roughly 78,000 or 79,000 roundabout operations. However, we've gone from real numbers to complex numbers. So now my multiplications in the frequency domain are all complex multiplies. Even though I've got real samples for the filter coefficients, I've still got complex numbers there. So it's going to cost me about 8,000 operations to do the multiplication. Inversion of the Fourier transform costs me the same as going forward. And now if we start breaking down the number, our 23 blocks per second becomes approximately 4 megaflops per filter, down from 69. So our Fourier transforms just lopped an order of magnitude, more than an order of magnitude, off our operations. How do we do the head then? Well, the head's pretty straightforward, really. You grab a dummy, stick 2 microphones in its ears, and then you go and record the speaker playing back to the dummy. Now, this is actually complicated if you only want an HRTF. If you're happy to get both the room and the head in the same stage, it's really straightforward because that's all you need to do. But we often want head-related HRTF sets or head-related transfer functions that are independent of the room. So we go and do this measurement inside an anechoic chamber so that we only record the influence of the head and the shoulders, not the room as well. Once we've done it, that recording behaves very much like that room impulse response. It's a series of samples, we just turn it into FIR filters. And so we can apply the same process. If we're going to do it in the time domain, it costs us a heap. Do it in the Fourier domain instead, costs us barely anything. The other bonus is, if I want to do both the HRTF and the room impulse response, I don't need to go back and forth in and out of the frequency domain all the time. I can go one step into the frequency domain, apply the BRIR, or the room impulse response, apply the HRTFs, 2 lots of multiplications, that will do a single Fourier transform back out. Hey, if I'm really, really good at what I'm doing, before I even start the operation, back at the factory, I'm going to do the multiplication between the room impulse response and the HRTFs, so I don't do those at runtime. So now I have a binaural room impulse response, a BRIR, and it's one set of multipliers that apply both head and room in one hit. So we did. So some of you will know Overwatch, some of you won't. That's where the latest Atmos Headphone Virtualizer is. So that's what my team delivered. I suppose January last year I was down in the Blizzard office working with the guys down there to tune up the get headphone virtualization working inside their game engine. So Bit of self-promotion there. That's kind of the fun stuff we do. I get to play Overwatch at work, okay? Just to be clear. So that's kind of headphone virtualization. I was going to move on to the second case study, but were there any questions before we do?
When you're taking the room impulse response,
Yep.
what kind of signal are you outputting from the speaker?
Right, so you've got a few choices. You could do it if you could create an ideal impulse. So literally something like a single spike of energy. But that's hard to realize in the real world. So you don't get good quality room impulse responses if you try and do that. So typically you use one of two types of signals. Either you use a chirp, which is a frequency sweep. And the benefit of frequency sweep is you get all the frequency information. You've got something you can time align to reasonably easy. But you don't get any cross-harmonic interactions. So it relies on the space being a linear system, which is usually pretty true. So it's a reasonably good and very easy to work with signal. If you need to excite all the frequencies simultaneously, you use a noise burst instead. And if you use a noise burst, you give yourself a few extra problems in terms of alignment and being able to analyze what you record. But if you've got any suspicion that there's something nonlinear happening in the space, you've captured all the frequencies simultaneously activated. So you can work with those nonlinearities.
So any kind of signal that you output which has a finite duration, how do you work out which bit of the signal the echo is coming from?
So this is why the actual analysis of that, if you've got a frequency sweep, you can do a transformation of, you record it in the time domain, you can do a transformation back into the frequency domain and you look at it, and that gives you the frequency thing. And you may want to do some windowing on the recording to make sure that you're getting the right stuff. But yeah, it's not a simple, there's not a single simple answer. It's a couple of steps in processing what you record.
Right, so your linear response assumption is assuming that you're not getting any harmonics or anything like that off the...
Yeah, there's nothing active in the space, which, to be clear, is true for pretty much all spaces. The reasons you might want to move away from chirps is if you think that the speaker you're actually playing them out of might be in distortion mode, in which case, change your speaker.
What would something non-linear in the space look like?
Well, distortion in the speaker you're playing it out of, distortion in the microphone you're recording it, so maybe you've got a cheap microphone. If you had a moving baffle that had a spring sitting beside it, actually that's still going to be linear. If you had an actuated baffle in the space, there are some weirdnesses, but generally it's not, you don't need to worry about it. All right? Not a big thing to worry about. Usually step one, fix all your recording equipment so you don't have to worry about these problems, then use a chirp. All right then, so we should keep moving. So the second case study I wanted to give you a brief taste of is perceptual audio coding. Perceptual audio coding is all about the idea that if we start with uncompressed audio, we've got lots of bits and a high bit rate, and in practice we can't deliver that to a consumer. We don't want to be delivering it in a streaming fashion. You can't put it on a disk easily. You want to do some compression. CDs with stereo PCM data on them was the last time you probably are ever going to receive uncompressed audio in terms of a commercial product. All of the products these days, whether you're streaming audio or you're buying a DVD or a Blu-ray, is going to be compressed. Of course, there are people making or trying to make a business out of delivering uncompressed audio. So HD Tracks and Tidal are both trying to deliver uncompressed audio, but in reality is this stuff is what rules the roost. So what kind of compression ratios are we talking? Around about a 10:1 compression ratio is what we get out of AC3. AC3 is now what I consider last generation audio codec. With the advent of AC4, we're doing a bit better than that for multi-channel kind of theatre productions or home theatre delivery. just as a query, what other kind of compression techniques or compression algorithms have you guys come across? There's at least one I'm expecting you to be able to name. MP3, yeah. JPEG, right? AAC, yep. These are all good audio and video or audio and image compression formats. OGG, yep. FLAC, is FLAC compressed? No. Right, that's not true by the way. How is FLAC compressed? Actually, that's the right question to ask. Lossless compression. What's the difference between lossless and lossy compression?
Lossy is like you're losing some of the frequency.
You're throwing out some of the information. Yep. So you can't, when you do lossy compression, you can't get back to what you started with, exactly. So does zip use lossy compression? No. Zip is probably the most common compression technique that people use for lossless compression to pack down your file sizes. When you use zips, or if you were going to zip up a CD track, do you think you would get 10:1 ratio in compression? Any ideas where you might get to with a lossless compression system applied to audio? 2:1 if you're lucky. 2:1 if you're lucky. So one of the things that became apparent very early on in the audio compression world is if we want to reduce data rates, lossless compression isn't going to work particularly well, and we needed to start thinking about lossy compression. And that's where perceptual audio coding comes in. Basically, we want to be able to throw away part of your music or part of your audio, but we want you to still love what you hear when you get it back. We don't want you to be able to notice that we threw stuff away or that we didn't encode it accurately. All right? And that's the fundamental thing that drives the word perceptual in this. The measure of whether the coding is good or not is whether you can perceive the stuff we threw away as missing. Do you hear the noise we introduced? Because we're going to introduce noise. The working out of that is what we then fall back on some perceptual science to answer. So here's your basic block diagram for perceptual audio coding. Do some kind of time/frequency analysis. Do some kind of psychoacoustic analysis. Work out how we're going to distribute the bits that we have available for the signal that we're going to encode. Quantize, and we know quantize is a noise-inducing or lossy process. And then at the end, we'll do some lossless compression as well, just to squeeze the last bits out of it. So entropy encoding is lossless compression, zip. But we're going to focus in on this psychoacoustic analysis block to kind of give you a picture of what's going on. So, first thing I want to do is get you to watch a video. And, whoosh, that's bright. All right, so watch this carefully and try to work out what syllable the lady is repeating. So eyes open, carefully watch how she's saying it and decide what she's saying.
Okay, here we go. Baba, Baba, Baba.
All right, what's she saying? All right, what'd you? Aza? Gaga? What else? Anyone hear anything else? Dada? Father? All right. All right, now close your eyes. Close your eyes.
Baba, Baba.
Open them.
Baba, Baba, Baba.
All right, so what's she saying? Right. This experiment is about teaching you that your ears don't work alone. All right, so this is something called the Mcgurk Effect. You can read the write-up there, it's quite interesting. But basically, what you hear or what you perceive is a combination of what you hear and what you think. And so we can mess about with that quite a lot. Once you get a brain involved with stuff, you can really do a lot of fun things in terms of lying to it repeatedly. So while we hear one thing when we see what's going on, we hear a different thing if we rely only on the perception. And that tells us that our ears can't be trusted. And we're going to exploit that fact that what we hear is always interpreted through our brain's filter. And that's why we talk about perception rather than hearing. All right, just to be clear. Right, so which bits are important, which bits aren't? Psychoacoustics begins with the recognition that almost all of the things we experience are not linear quantities, and they're all subjective quantities. So whereas I can take a sound measurement device, recording, and I can calculate the RMS, loudness, that's not loudness, that's just sound pressure volume. If I want to understand how loud that sounds, I have to understand how humans perceive loudness. So things like pitch in music is an expression of frequency, but it's not the same as frequency. All right? We can't say that pitch and frequency are the same thing because there's perception involved with pitch. So things like pitch are measured in terms of things called barks or mels or ERBs rather than absolute frequencies. Now you can look up what frequency is middle A, and even there you'll get some discussion, but most orchestras use A440 rather than 441 or 442, which is some of the alternatives. But then how we hear that is part of what we care about. Most importantly, there's two types of lies that our ears tell us. The first is frequency masking. And frequency masking works very easily when we have a loud sound at a narrow band in the frequency space, and it will make us not be able to hear other sounds close to it in the frequency space. All right, so we have a loud masker, hear the loud masker, bit over 0.2. And if there was another tone or sound occurring just a little bit lower in frequency, but also lower in amplitude, we wouldn't be able to hear that at all. We could literally excise that completely from the signal and you wouldn't miss it. This masking, this frequency masking, is the most used effect inside perceptual audio coders. It's have a look at the signal, turn it into the Fourier domain, analyze it to work out what the threshold of masking looks like, and then anything sitting below it, we don't have to care that much about. So we can be messy, we can color outside the lines when we code it. The other side is the flip side, it's the time domain equivalent. If you have a really loud sound happen at one point in time, you're not going to hear quieter sounds that occur just after it. So if we have a time 0, something loud occur, then for a period of time afterwards, we won't hear softer sounds occurring. And that sounds like good fun, but the really, really wacky thing is have a loud thing occur at some point in time, and you won't hear things that were softer that occurred just before it either. So there's something called forward masking and backwards masking when it comes to temporal masking. So these two effects are what combine to give us the basic of the psychoacoustic analysis we want. Time frequency is just about breaking it up into blocks for analysis. The reason it's called time and frequency analysis is the size of the blocks change. The size of the blocks change because we want to be able to take advantage of the temporal masking curve. So if there's been a really loud, sharp sound, an impulsive sound, we want to analyze that with a really short period of time because we can be quite messy about encoding that. If it's a long, constant tone going on, we want to analyze that over a long period of time and treat most of our work in the frequency domain. So our time frequency analysis switches between short blocks and long blocks, ultimately creating Fourier transforms for us to apply masking curves or calculate masking curves with. So once you've got your time blocks sorted out and you've worked out where your masking curve looks like, you've got a pool of bits that says for this part of the spectrum, I'm going to quantize this with 3 bits per sample. Or this part of the spectrum I'm going to quantize with 8 bits per sample. Remember our commentary back about how many bits, kind of the relationship between bits and noise, quantization noise? That's what we're relying on. So we know every time we give another bit to a section of the spectrum, we're increasing its, well, we're reducing its quantization noise. With the bits we don't care about, we're happy to have really high quantization noise, so we don't give them many bits. For the sections we care a lot about that we can hear, we want to make sure we give enough bits that we can't hear the quantization noise. And that's essentially the trade-off that happens inside bit allocation. Just to give you kind of a practical plot of what a masking curve looks like. So the light grey curve is the actual spectrum of the signal. And every time it drops below the dark black curve represents where we have masked out what was actually happening there. You know, the first things you notice is that in the high frequency, sounds have to be very loud, have a lot of energy in them before we'll even hear them. So a lot of the time you can just spend no bits whatsoever up in the high frequencies. You know, essentially send band limited audio, and people can't hear it. So we use that masking threshold and the bit allocation to determine how we quantize the signal. The last trick of actually turning that into entropy coding and into a bit stream is just kind of mechanical, same as your zip. You're going to use zip practices. So I think I've pretty much said most of that, just going through the bit allocation process. Then the quote-unquote simple stuff, which is decoding, is just go the other way. Recreate the frequency representation, invert the block transform. Then, because you've done all this kind of throwing away, you might want to do some post-processing to try to enhance what you've sent. For example, we were talking about harmonics earlier. You know, I know that when a fundamental frequency for a note is produced, there's quite common for harmonics to exist as well. So maybe when I encoded it, I didn't bother encoding the harmonics, but once I do a decode, I might detect that there were harmonics missing and try to put them back in, guess at where they were. And sometimes that worked quite well. But that's it. That's how perceptual audio coding works. Work out how much you can lie to the brain, and then write down the bits. Which really gets us to the end. So are there any final questions? Sure.
How consistent are these perceptual curve functions on frequency between people?
It's a good question. There is variability. Every person is different. There are also small percentages of the population that are superhearers. I mean, you hear about kind of standout capabilities within individuals. The reality of how that gets interpreted is mostly you shoot at the average. So there's a large body of psychoacoustic research that characterize what the average looks like. And that's what you use as your guiding principles for design. When it comes to actually getting a codec and taking a codec from kind of the research workbench out to the world, so things like AC3, AC4, the MPEG codecs, the MP3 codecs, all that stuff, to become public standards, they go through standardization organizations like the ITU. And in that process, they go through very strict and controlled listening experiments to characterize how well they work. And so that's done in a way where there's a sample of people coming in and actually evaluating their perceptual quality. And whether they work well enough for enough people gets basically comes out of those kinds of experiments. So, yeah, to be clear, one of the things kind of didn't mention about perceptual audio coding, if I give you enough bits, you can do it and you won't hear the difference. But by the way, we're never going to give you enough bits. Everyone always wants to deliver with less bits, lower bit rate. So it's always a trade-off between how much quality are you willing to give away to reduce your bandwidth. And a lot of the listening experiments, you can hear that it's been coded. That's a skill that you can develop quite easily. If you go and listen to MP3s at low bit rates, you'll start hearing the artifacts. But there's always just that business trade-off. Someone will choose, hey, this is the bit rate we've got. Can you give us a good enough codec to fit into that? And they'll accept the loss in quality.
Do you use psychoacoustics to make things seem louder than what they really are?
You can't make something seem louder than what it is. What you can do is you need psychoacoustics to answer the question of how loud something is. So, for example, back now more years ago, it's settled down a lot now. You always used to sit there, and when the ad break came on, you would go, hey, these ads are really loud. And the question of is, why are they really loud? Well, the way that you make something sound loud without increasing its RMS level is you compress the soft sounds up. And you do it in a way that the RMS stays the same, but because you've compressed the loudness into a narrower band, it can sound louder. So these are more tricks that you use to get around the objective measurements. So if loudness or monitoring on TV stations is done objectively, they just measure RMS, then it's very easy to fool them and make something that has the same RMS sound louder than something else with the same RMS. That's why you then bring psychoacoustics into the game so that you can undo that process. Because we understand how loudness works, we can accurately predict loudness based on the signal rather than relying on an RMS dumb measurement. So it's more that psychoacoustics saves you from that problem than enables it. The one thing that you can do with psychoacoustics is really fun is backmasking. People can Google backmasking. It's an LP trick, so a vinyl trick. So records, black round things, you guys seen them? No. All right, at this point then I think I'd better hand over to Steve, who's going to talk internships.
Thanks, Mike. And thanks to Alex as well for having us today. I appreciate giving us one of your lecture spots. Can everybody hear me okay? Okay. I'm quite loud anyway, so I probably don't even need a microphone. My name's Steve Byrne. I'm the recruitment manager for Dolby in Australia. And I'm here today to talk to you guys about internships. Show of hands, who's interested in doing internship, looking at internship over the summer period next summer? Yeah, so quite a lot of people. Why? Why are you interested in doing an internship? Well, what's money? There you go. That's it. Very good answer. Very good answer. Yeah. So money, absolutely. Any other reasons why you might look to do an internship?
Industrial training.
Experience, industrial training. Yeah. Well, obviously there's a requirement on the engineering side to do that as part of your degree. Yes. It sounds awesome. It does sound awesome. Our internships sound awesome anyway, which you'll bet to find out. Yeah, look, they're all really, really good reasons. And when we looked at the internship program at Dolby, one of the things we wanted to do was make sure that you learn something. And that's a really important thing as well. The internship program is set up to be very practically focused and improve your skills as an engineer, which will make you more employable, hopefully for Dolby in terms of full-time opportunities, but just in terms of readiness for the workplace and becoming a stronger engineer. So how the internship works at Dolby, it's a 12-week program running over the summer period, so generally from the end of November through to the end of February. It's paid, so yes, absolutely, that's something that you definitely get, and we're quite competitive on that side of things, so you will definitely be looked after on that front. And you will also get a week of annual leave as well. You get a week of leave, plus we close between the Christmas and New Year's period, so you get that time off as well as paid leave. So you get a little bit of time to have a bit of a break and also some time to work at Dolby and grow your skills as an engineer. So what will you actually be doing when you work for Dolby? You will get embedded into one of our teams. We've got 4 main groups at Dolby. And you'll get embedded in a team there and actually get to work on some real-world product that goes out into the world and becomes part of a product for Dolby as well. So it's a fantastic experience to get at undergraduate level, that you'll get the exposure to be able to work on an actual product. It's not glorified data entry. We're not going to ask you to go and get the coffee for everybody. Well, I don't know. Mike, did you ask anybody to go and get coffee for you?
Not against their will.
Not against their will, no. Yes, absolutely. What do we look for? We look for a broad range of skills. We've got various different teams that focus on different things. So we look at everything from signal processing, so DSP. We look at embedded software engineers, so people who've got C skills and some Python as well. We also look for engineers that do C++. We've got one of our products, a Dolby Voice product. We need engineers in that group who can work on low latency, high performance C++ because it's a real-time voice system that gets used at an enterprise level as well. So writing efficient C++ code is really important. So there's a range of things. We're also starting to do a lot more on the cloud side of things as well. Some of our services are now being hosted and deployed in the cloud. So we look at people with Amazon Web Services skills or various different AWS or web services web skills as well. So it's quite a range of things that we look for. But most of all, we look for smart people who are interested in some of the things that we do. And Mike's given you a little bit of a flavor for some of the stuff we do on the audio side of things. We also do some work on the imaging side of things now, which is really exciting for us, the Dolby Vision and Dolby Cinema side of things. And we work on a really broad range of platforms, as Mike mentioned as well. So everything from the cinema through to at home in your lounge room to on-the-go mobile devices, tablets, which is increasingly where people are starting to work as well. So in terms of when we're looking to hire people, the applications open in a couple of weeks. So what I'd like to do would be to send Alex the links. Maybe you can forward them on to the students when the roles are open as well. And then afterwards, we'll be taking the applications for about a month. And then afterwards, we'll be drawing up a short list and organizing interviews. So it's a straight to interview process. So you'll do a phone interview with an engineer, and we'll put you through your paces a little bit on the technical side of things. And then we'll draw up a short list from that again and decide who we want to bring in for a face-to-face interview. And that takes about an hour and a half. You'll meet with a couple of our engineers. Don't worry, we're very friendly, we don't bite. And then, but we want to get an understanding of your problem-solving abilities and if you've got the basics on the coding side of things as well, depending on which group you're going to be working in. Now, does anybody have any questions at this stage? Does anybody? Yes, go ahead.
Will it be open for international students?
I'm sorry, I didn't catch that.
Will it be open for international students?
Yes, absolutely. Yeah, no, absolutely open for international students as well. So we don't restrict on that side of things. We just want bright people who are interested in the type of things that we do and want to work for Dolby. Yes.
So is it specifically just C++ and C programming?
They're the main languages that we tend to use are C and C++, plus Python. We use Python quite extensively as well on the scripting side of things. As I said, we're starting to do a little bit more on the web side of things, so having some web skills is useful depending on what we're looking for, but predominantly C and C++ are the main languages that we look for, so yeah. And if anybody has skills on the network programming side of things as well, that can be useful for a couple of the teams that we work in as well. Any other questions? Yes?
Do you normally take graduate roles or do you promote regular internships?
Look, that's a very good question. And the internship program is seen as a little bit of a feeder program for full-time opportunities for Dolby. We don't have a graduate program as it stands at the moment. What we tend to do is hire people to be full-time engineers at Dolby. So they come in as a graduate, but not in a dedicated graduate program. We like to embed people in the team and get them really working on a project straight away as well. So, and we've got a very good track record of converting people from interns into full-time employees. You know, so it's not guaranteed if you do get a space on the internship program that you definitely will get a job at Dolby. But you know, if you do a good job and we have roles available, which we usually do, you know, why would we look at external people if we know if you're a known quantity and you've done well in the internship program? So absolutely. And it's also a good way to make contacts in the industry as well, you know, so you never know what doing an internship could lead to, even if it's not in a position with Dolby as well, although we hope that it is. Any other questions? All right. Fantastic. Well, listen, thank you so much. Oh, sorry, you've got a question.
Sorry, could you expand a little bit on the role of someone doing embedded software when you do it?
The projects will vary depending on what's going on for a particular team at any given time. So it's hard for me to specifically say you're going to be doing X. On the embedded side of things, you'll generally be working on turning software framework stuff is a lot of the stuff that we do. So a lot of the framework that supports the DSP side of things as well. And actually the process of turning something from an algorithm into a piece of software that's then going to go to our customers as well. Dolby's predominantly a software licensing company, so how we make our money is we will create the software, it'll get licensed to our customers, which is very, very broad. Dolby technology is in over 9 billion devices around the world, so it's really broad. And then it will get integrated onto their devices as well. So a lot of sort of low-level software engineering work goes into getting it ready to go and give to our customers.
Yeah,
Right?
Maybe I can add just an extra comment there. I mean, the typical technology life cycle in Dolby begins in our research departments. The research departments pass it on to an engineering team or a platform development team. Their primary job is to take a signal processing algorithm and convert it into an engine. This is typically why we're working in C, because that engine needs to actually work across a broad range of devices. So the same algorithm needs to be turned into a library that we could compile and put into a product on a mobile phone, on a set-top box, inside a TV, into a PC. So when it comes to what's considered embedded for us, everything we write is considered embedded. So all of the kind of fundamental engine stuff is written in a way that has to be embedded friendly. It has to be performant. So it's not by chance I talk about megacycles and MIPS and stuff. That's kind of central to the job of creating a commercial implementation of an algorithm and signal processing. And then that engine gets picked up by our product teams. So this is kind of as the life cycle goes. Those product teams are the ones working in kind of specific devices or creating a specific endpoint that might go into. So the team that's integrating X into Windows, or the team that's integrating Y into our cinema processor. And they think perhaps a little bit less in the generic sense and more specific around their environment. So depending on kind of where within that life cycle, the team you might get embedded with kind of is a measure of where you'll what amount of embeddedness you're thinking about.
Fantastic. And just on that as well, in terms of the positions that we're looking to fill, we're looking to fill DSP software engineering positions, some straight software engineering positions which focus more on C++. And this year we're going to be looking at software engineering and test internship positions as well. So, and they're really interesting internships because you get an understanding of how software is tested thoroughly, and that's very important for a company like Dolby as well, in particular, given that we license our technology out and it has to work first time out of the box. Is really important. And again, it's also something that there's not really a huge amount of focus on at undergraduate level as well, so it's an interesting role to do as an internship. So when I talk about the broad range of skills that are there, you don't have to have all of the skills to be suitable for all of the positions. Again, depending on which role that you want to focus on the one that's got the best match of skills that you have. So you don't need algorithmic skills for necessarily all the positions at Dolby. So yeah, look, I'm available to come and have a chat if people want to have a chat to me individually afterwards. My card's here if you want to take that away, and I've got a little bit of Dolby swag if you want to take that away with you as well. So thanks so much for your time, and best of luck.